In this video, we'll talk about TriNeRFLet paper, which we present in ECCV 24 at Milano, and its main idea is to represent a neural lattice field using 2D wavelet feature planes. A neural lattice field, or as known as NeRF, is about learning an implicit function f that represents the 3D scene. F takes as an input x, y, z coordinate, the gamma phi direction, and output the density at this point, sigma, and the RGB color. So, taking a look at the given pixel, we take a look at the points that reside at the ray that passes through this pixel, sample the density and color at these points using f, and using these values, we can estimate the final color of the pixel. Then we compare this color with the ground truth K1 and calculate and you learn the parameters of f theta by back propagation. Triplane is about taking the XYZ coordinates and projection into three perpendicular feature planes, and these projected features is the embedding of XYZ instead of the frequency embedding. TriNeRFLet is about learning these planes in the wavelet domain. So we have here the wavelet features. In the upper left, we have the low resolution, the low resolution one, and in the other channels we have the higher frequency features for the different resolutions. We take these wavelet features to 2D inverse wavelet transform in order to build the feature planes, and then after we obtain the feature planes, we render the scheme as a regular triplane in order to get the estimated images, and then we compare them with the ground truth images in order to learn the parameters of this scheme, which are the wavelet features and the MLP. We also add the sparse regularization to the high frequency channel, since we know from the sparse theory that high frequency channels should be sparse. Here is an example of the learned wavelet features of this shape scene. As we can see here, here are the wavelet features, and here are the reconstructed features from these wavelet features. TriNeRFLet super resolution scheme operates as follows. We take as an input low resolution images of a given scene, and we want to be able to render the same at high resolution images and also be able to render new views as well. So we have here all the wavelet features. We take a look at the low resolution subset of it, and we learn this low resolution subset using the low resolution input images. Next, after we learn the low resolution subset, we take a look at the all wavelet features and learn all wavelet features using an estimated high resolution images of the scene. We will see next how we do build this estimated high resolution set. And since the low resolution version is a subset of the all wavelet features, it guarantees that the high resolution scene stays faithful to the low resolution one. So we build HR set as follows. We take all wavelet features, we render it in high resolution. First, we will have an upscaled low resolution images that does not contain any high resolution features. We take this image, add to it noise, and plug it into stable diffusion upscaler while conditioning it on the ground truth low resolution image. The result of the stable diffusion upscaler is a refined version of this image that contain high resolution details. And then we take this image and add it to the HR set, which will train the TriNeRFLet high resolution on it. And then each several steps we refresh HR set with the new images in order to have more 3D consistent details. So here is an example for our method. Here we compare TriNeRFLet with Triplane, and as we can see, TriNeRFLet manages to remove all the artifacts of Triplane and is competitive with the current state-of-the-art reconstruction method. Also, in this example, as we can see, TriNeRFLet manages to remove almost all the artifacts in Triplane. And next, if we take here at the super resolution, it is easily observed that our method does a pretty good job in upscaling a 3D scene, as you can see here in the Blender dataset and next on the LLF dataset. For further details and examples, please see the paper and the website. Thank you.